Okay, so today we are going to shift focus a little bit and to see where we are going, let us just do a quick recap of what we have done so far. We started with state space search, and then we went on to heuristic search, and from there we went to optimization. And the idea was that the idea of optimization came in because we said that instead of looking for the goal state, we will try to optimize the heuristic value or the evaluation function or the objective function, as the case may be. And the idea of using heuristics was to find solutions faster. Because we discovered that search spaces tend to grow exponentially, we were looking for a function or some kind of heuristic knowledge which comes from the domain, which will guide the search towards a solution and not go off in other directions, and in the hope that we will find it faster essentially, because we do not want to run into exponential times. Yeah. So, today we want to shift focus and look at the other aspect. So, once you find a solution, so let us say you are solving problems in some domain, or let us say it is a logistics domain, or you are running a courier company and you have to send people all over the place to collect parcels and deliver parcels and things like that. The solution that you find has to be executed and has an associated cost essentially. So, today we will shift focus to finding solutions which have an optimal or least cost solutions essentially, and that is critical in many domains. To take an extreme examples, if 10 years from now you start a company in which you are setting up a colony on Mars, then you can imagine that the cost of each trip is going to be significant, and you would like to have a solution in which there is a minimum number of trips essentially. So, maybe on the way you stop on the moon or something like that, or more coming down to earth, if you are traveling, if you are like a traveling salesman going through a few cities, you may want to optimize the cost of your tour, or if you are using some vehicle, let us say daily in a city because of your job. Now, unless you happen to be a politician in the government or a bureaucrat in the government who get apparently unlimited fuel supplies, you would be worried about the cost of fuel and you would want to find solutions which are optimal essentially. So, our focus is going to be on finding optimal solutions. Now, of course, one might ask as to how is this different from the optimization that we have been studying so far, because for example, we said that we want to solve the TSP when we are looking at an example of optimization. So, it is not really different, it is the same process. It is just that I want to be clear on the motivation as to earlier we went through this process of devising the idea of a heuristic function and trying to find optimal solutions for that, or trying to find optimum values for the heuristic function, and in the process we sort of wandered into optimization, which is what we are interested in, but we never looked at solutions which guarantee optimality. We only looked at randomized methods like simulated annealing and genetic algorithms and ant colony optimization, which are likely to work most of the time, but not necessarily guarantee optimal solutions. So, what we want to do now is to look at methods, deterministic methods, which will guarantee optimal solutions. So, these are the two different aspects of problem solving. One is how long do you take to solve the problem, and a heuristic function is devised to speed up that process, and the second aspect is how good a solution you find, and that is a aspect that we are going to focus on today. How to look at optimal, how to find optimal solutions. So far we have not had a notion of cost in the solution finding process, and whenever we spoke about quality of a solution, we said the number of steps or the length of the solution. So, now let us introduce cost, and which means we will introduce a weight for every edge in the search space, and then we want to find solutions which are optimal cost. So, it is like finding the shortest path, and that is the abstraction of all these problems that we are looking at, essentially finding shortest paths in a graph. So, let us start with a small example graph, just to illustrate the algorithms that we are looking at. So, let us say this is a start node, and then you go to some node called A, and the cost of going to that node is 4, or you can go to B, and the cost of going to B is 5, and the cost of this edge is, let us say 3, and then you have, let us say a few more nodes C, D, E. Let us give some cost to these. So, let us say this is 6, and let us say this is 8, and let us say this is 4, and let us say this is also 4, and let us say this is an expensive edge costing 15, and this is 2, and let us say this is a goal node that you want to reach, and the cost of going to the goal node from here is 2. And so, let us say there are some more edges which I am not drawing, because we do not want to have a exploding search space, but let us say this is the example. You want to start from S, and you want to find a path to G which is of the shortest path essentially. So, the general algorithm that we will follow can be abstracted as follows, that refine or extend the least cost, and I must emphasize least estimated cost, because we do not know the actual cost, So, the main problem solving step, which is basically very similar to what we were doing earlier. We have a move gen function which generates successors, and you have to choose one of them and so on, but we can view this now a little bit more abstractly, in the sense that we are working in a space of possible solutions. We do not have all the solutions, we have some of them partially defined essentially, and with every partial solution we have an estimated cost, and when we say estimated cost, we mean an estimation of the cost of the total solution, if that were to be completely refined. So, we will use the term refined to say that if you have a partial solution and we add a little bit more information about that solution. So, for example, if you are solving a TSP, if you have put in 5 edges, and if you add one more 6th edge, then that is a little bit more refined. So, in the process of you keep refining partial solutions till you have a complete solution, and then you would stop, and the algorithm that we will use is that extend the least estimated cost partial solution till such a solution is fully refined. Because in the end we are interested in a solution, complete solution. So, actually I must clarify what I mean by this, till such as, and we will see this as when the example comes out, that till the least cost solution is fully refined. Instead of writing that, I have just written till such a solution, but you must read this such a as a least cost solution is fully refined. So, just imagine this situation where you have some partial solutions and some and at least one fully refined solution or more than one fully refined solutions, and you have estimated costs for them. Now, for fully refined solutions there is no notion of estimate, you actually know the actual cost, whereas only for partial solutions you have to estimate cost. Now, if one fully refined solution has the lowest cost, then we will say we can terminate, that is going to be the basic idea, and we will discuss this as to when is this idea sound or when is this idea guaranteed to give you the shortest solution. So, this is the loop that in which we will operate in the next few classes. It is just that our notion of partial solution may change as we go along a little bit. So, let us look at this from the state space perspective as we have done earlier, and when I look at this algorithm, you must keep in mind that the similarity with Dijkstra's algorithm essentially. So, I take it that everybody is familiar with Dijkstra's shortest path algorithm, which takes a single source and finds shortest paths to the rest of the graph essentially. So, we are in some sense going to mimic that algorithm, but our goal is not to find solutions to all the nodes, but we will be doing something similar essentially. And the algorithm that we are looking at is called branch and bound. So, by branching we mean this process of refinement or extension, and by bounding we mean excluding some solutions. So, remember what I said, that at the point at which we terminate, we will not bother about some solutions which are not fully refined, because we would be able to exclude them, or they are gone beyond some bound that we are working with, and we do not need to refine them any further. So, this general idea is called branch and bound, and it is so let us first simulate this algorithm on this graph. So, you start with the search node, and it is very much like the other algorithms that we have seen. We generate its children, in this case A and B, and in this simulation we will assume that we are not going to remove duplicates essentially, okay, because it is possible that we may later find a shorter path to a given node essentially. So, we do not want to say if you have seen that node, do not generate it again essentially. So, you can say this is searching over paths. That instead of saying that we are visiting a node, for example D or C, we will say we are inspecting a path from source to D or source to E, and we are looking at different possible paths, and we will. So, if there is one path S A D, then this is a different candidate from another path which is S B D essentially. So, we will treat them as separate. So far we are saying if you have come to D before, do not bother, you have already, so do not put it into open, that is what you used to say. Now, the cost of S is 0, the cost of this path is 4, the cost of this path is 5, because that is the cost of those edges. The algorithm is simple: refine or extend the least estimated cost partial solution. So, instead of saying that we are taking the cost of the complete partial solution, an estimate of the complete partial solution, we will work with the known cost that we have, which is the cost up to A essentially. So, as far as we are concerned, we have two partial solutions here, one goes from S to A, the other says goes from S to B, this one costs 4, this one costs 5, and we will say that this is better than us. So, we do not have any sense of direction. So, this is a simple process we will follow. So, we will say that this has been inspected. In Dijkstra's algorithm you would do something very similar. So, I will just do the two algorithms in parallel. In Dijkstra's algorithm you would initialize S to cost 0, and everything else to cost infinity, and maybe in some versions of the algorithm, some descriptions of the algorithm, you will color them white and you will color this or color everything white to start with, which is like putting them on open or something like that, and pick one node from there. So, there is a stage of relaxation in the Dijkstra algorithm, which says that once you relax this node or once you inspect this node S, you relax all edges going out of that, which means this cost originally was infinity and now it is reduced to 4, because we know that you can get from S to A at 4. So, we revise this cost to 4 and revise this cost to 5, exactly what we are doing here, except that in Dijkstra algorithm you would do it on the graph itself, and then you would pick the lowest cost node. So, Dijkstra would also pick this and color it black, for example, and then relax these 3 edges, which amounts to saying that we will generate these 3 edges. So, one simplifying assumption while drawing we will make is that we are not going to go back, we are not going to allow loops, because we know that loops are only going to increase the cost. So, if I go back, go from S to A and A to S, it is not going to help me in any way. One assumption that we are working with, like Dijkstra does, that costs are all positive here. So, pick the least cost node S A. So, let us say this amounts to coloring it black here. So, Dijkstra also would color it black, and there would be a pointer pointing back to this, and then Dijkstra would color this one black, and try to, when you relax this edge, you find that 4 plus 3 7. So, it remains like that, whereas this becomes 8. So, this is an arrow which comes here, this becomes 19 and an arrow comes here. So, there are these costs associated with nodes which I am not writing there, which I am writing here. So, from A you can go to B, or you can go to D, or you can go to E, and the costs are, as we said, 19 for this, D is 12 and B is 5. So, very similar to what we were doing in heuristic search, always pick the lowest cost node, except that when we are doing heuristic search, it used to be the lowest heuristic value node. Here it is the lowest known partial solution cost. So, this is, sorry, this is not 5, this is 7. From S from A to B, then if you come like this, it is 7 essentially. So, then you pick this B, and from B you can go to C, or you can go to A, or you can go to D. If you go to C, then you have a cost of 9. If you go to A, then you have a cost of 8. If you go to D, then you have a cost of 11. So, this process continues. Then let us do a couple of more rounds and then we will stop. The lowest node now is B. So, we do this. So, as I said, we will not allow loops. So, we will not allow A or B to be, because A or B is in the path here. So, the only thing you can do is go to C or to D, C, D. So, 7 plus 4, this is 11, and 7 plus 6 is 13. So, you can see we have found 2 paths to D, one path costing 11 which goes from S to B to D, S to B to D which is cost 11, the other is from S to A to B to D which costs S to A to B to D which costs 13. Let us say there is another edge which I had not drawn earlier, forgot to draw earlier, this is costing 7 units, let us say. Now, this is A is the lowest node that I can expand, and from A I can go to, so I can't go to S, I can go to B, I can go to D or to E, and the cost of going to D is 16 here, and cost of going to E is 23 here. So, I have done away with A. So, now something interesting is happening, that I am going to expand C. So, C and D are interesting because they are the 2 nodes which lead us to the goal essentially. So, at this point this node C has become the lowest cost node. So, this is 9, 16, 23, 11, 11, 12, 13, 19. So, I expand this C and from C I can go either to D along this path or I can go to G. So, if I go to D from here, it is going to be 9 plus 4, 13. If I go to G from here, it is going to be 9 plus 7, 16. So, I have found one path to the goal. So, let me highlight that path. I am going from S to B, B to C and C to G, and that is a path represented by this node G here, S to B, B to C and B to G. So, this is gone into closed. So, should I terminate, or if you go back to what Dijkstra would have done, right? Dijkstra, so what have we done? We have colored A, we have colored B, we have colored C, and we have not yet colored D or E. Now, if you look at this graph, there is a path going from S to B to D, which is 11 plus 2, 13. Now, that path is better than this path, which is of length 16. And if I want my algorithm to find the optimal path, I cannot stop at this stage, which is why we have this condition till such a solution is fully refined, and I said by such a I mean the least cost solution is fully refined. Now, in this case the least cost solution is this D and this C. So, let us say without loss of generality we pick D from here, and once we pick D from here we will add this. We have already seen C. So, from D you can go to G to C and to E. So, let us not worry about C and G. The cost, this cost from S to B is 5 and then another 6 and then 2, and we have this cost of 13. So, now we have added in some sense to open, if you want to say, this path S B D G to open, and we also have another path S B C G to open, but none of them is at the head of the queue. Remember that we will use something like a priority queue to implement this. Before we come to this G, we will exhaust this option of C, we will exhaust this option of D, and we will exhaust only these two options we have to exhaust. This one, because this is lower cost and this is lower cost. Once we expand them or refine them, we will get more expensive solutions, and at that point this G will become the least cost, and then we can terminate. So, this is the idea of branch and bound essentially, that what do we mean by bound here, that the moment when we expand this node with 13, we are going to bound, we are not going to be interested in this node with 19 or this node with 16 or this node with 16 or this node with 23. We, even though they are not complete solutions, we know that if we were to refine them, their cost would be more than 13 here, and we have found this complete solution of paths cost 13, and the partial solutions are of higher cost. Therefore, I can terminate at this stage. So, at the moment when you pick the goal node or the path to the goal node, you can terminate. So, let us look at the another example, which is the travelling salesman problem, which we are so interested in. But before I do that, I want to ask a question of you. I have used the term estimated cost here, and when I say estimated cost, I mean the estimated cost of the full solution, not the partial solution. Here we are working only with partial solutions. So, when you say the cost of this path is 12, we mean that to go from S to A and A to D is 12. It is not telling you how much it would cost to if you went to the goal along this path. Now, I am talking about that instead of using this exact known cost of partial solutions, let us work with estimated cost of full solutions. So, let us say the estimated cost of any solution is C and the actual cost of the same solution, and by actual cost I mean if I were to refine that solution completely is let me use the term C star. The question I want to ask is the mechanism that I use for estimation, it can do three things. One is it can give me a perfect estimate, in which case this would be I would use the equality sign C equal to C star, but that is only a wishful hope that you will find an estimate which is perfect. So, let us hope that let us say that we cannot find estimates which are perfect, which leaves us two choices, either greater than or less than. So, we have eliminated that choice because we have granted that we will never find such a estimate. Now, if I had a choice between an estimating function which underestimates the cost and a choice with a different estimation function which overestimates the cost. So, let us say C 1 and C 2 are such functions. So, that let us say C 1 is less than C star and C 2 is less than is greater than C star, always greater than C star. Which one should I use? In other words, while devising an estimating function, what properties should I take care to satisfy? Should I use C 1 or should I use C 2? How many people here feel it is C 2? And how many feel it is C 1? Okay. The rest are undecided or not awake. Anyway, just keep this in mind. I will ask this question in a little while again essentially. Now, let us spend a little bit of time on the travelling salesman problem again, and this time we are looking for an exact solution. Okay. Even though it is a NP hard problem, we want to look at methods which will give us exact solutions. So, maybe we can't solve very big problems, but at least for the smaller problems we want this thing. And we look at something called refinement search. And by refinement search I mean the following, that consider the set of all possible tours, that will be the root node of our search tree, the set of all possible tours, and then by some operator I will partition this set into smaller sets essentially. And what is an operator? One operator could be that choosing an edge, for example, and then in the process I want to refine search essentially. And I also want to talk about estimated cost. So, one thing that while I draw a small example you should think about is, given a problem, which means given a set of cities and the cost of edges between those cities, how can you estimate the cost of a tour? In other words, can you find a lower bound of a tour, or maybe if you are interested, can you find an upper bound of a tour, any tour? In other words, all tours are going to be greater than some lower bound or not? Can we find such a lower bound? So, let me write a small example. So, let us say we have these 5 cities, Chennai, Bangalore, Hyderabad, Bombay and Delhi, and so Chennai, Bangalore, Hyderabad, Mumbai I should say, otherwise there is always a danger, and Delhi. So, I need the edge cost between these cities. So, I am just drawing the edge a matrix to capture those costs. So, these are 0, the diagonal elements because you are already in that city. So, let us take some simple values. So, let us say between Chennai and Bangalore the cost is 300 kilometers, between Chennai and Hyderabad it is 600 kilometers, Chennai and Mumbai it is let us say 1000 kilometers, and Delhi is 2000 kilometers. These are not correct figures, but nevertheless. So, 300 given these figures, can you find an estimated cost? And I am asking you a specific question now, can you find a lower bound on the tour cost, which means that no tour can be cheaper than that cost. So, let us put in some more values, let us say Bangalore and Hyderabad let us say is 500, Bangalore and Mumbai is let us say 900, and Delhi is the farthest from everything. So, let us say 2100 here and 1500 here and just some random or close to random figures, and that leaves me with between Mumbai and Hyderabad. So, let us say that is 700. So, this is my matrix given to me H cost, and I want to find a solution for the travelling salesman. And my refinement search is going to do the following, that my route is going to be S, I will just call it S, and this is a set of all tours. And what I am asking you is that for this node S or route S, which consists all possible tours, what would be the cost that I would want to associate with that, which is the lowest possible cost that I can think of essentially. Now, obviously, you can say 0 is a lower bound, because definitely every node, every tour will have cost greater than 0, but I am not interested in such a trivial lower bound. You can even say 300 is a lower bound, for example, but I am not interested in that. The reason for that is that if I am going to do this branch and bound, I am interested in excluding candidates from my search space, and I can only exclude candidates if their estimated cost is higher than my actual cost of some known solutions. So, to see an example here, if I were to expand this known solution is cost 13, this estimated cost is 19. Now, this 19 is actually the actual cost of going from S to A to E, but I can be overly optimistic and say that is actually the estimated cost of going to G from this path essentially. The rest of the edges I have cost 0, no, I can be overly optimistic about that. So, I can treat this actual cost of going to E as the estimated cost of going to G via this path essentially. But even if that were to be the case, I know that the estimated cost is 19 and this actual cost is 13, and this is only going to increase as I refine the solution further. So, it can never become better than 13. So, I do not really need to refine that. I am going to, that is the bounding away, I am just not looking at that this thing. So, for such reasons that I should be able to exclude bad candidates as quickly as possible, I need estimated costs which are as high as possible. So, as I said, you can always give me 0 as an estimated cost or 300 as an estimated cost, but I am not interested in that because they will not exclude solutions from my search space essentially. You were saying something. Yeah, so okay, so but I am not interested in higher bound so much essentially. So, let us talk about a lower bound essentially. Lower? Shortest 4 edges. Why not 5? Okay. Yeah, but yeah, so that would give me what 300 plus 500, even assuming that I look at only the diagonal matrix, I mean a triangular matrix, 300 plus 500 plus 600 plus 700, that would something like that. But my desire is to get as high an estimate as possible. So, the general idea is that I want as high an estimate as possible, but it should be a lower bound essentially. These two things I must say. So, there are of course, I know that there are more than one way of doing it. So, we will just use one method here, which is that we will take the lowest two elements from every row essentially. So, I will take 300 plus 600 from here. So, I will take 900, I will get 900 from this row, I will take 300 plus 500, I will get 800 from this row, then these two which will give me 1100 from this row, 7 plus 9 is 1600 from this row, and 12 plus 15 which is 2700 from this row. I will sum them up and divide the answer by 2. What is the rationale behind this? Taking 2 lowest from every row. Yeah. So, in a tour every city will have 2 edges, one incoming and one outgoing, if you can distinguish between them, and we are sort of being optimistic here and saying that the 2 edges are the lowest cost 2 edges here, because they cannot be better than that. So, if the lowest cost 2 edges are taken from each row and we sum that up and divide by 2, because we do not want 10 edges, we want only 5 edges, we will get an estimate of the lower bound essentially. So, we follow this similar, this high level algorithm we follow, we refine the cheapest cost partial solution. In this case we have only one at this moment. So, we will refine that till a solution is fully refined. So, let us say we use some heuristic and we say that we will add a cheap edge to the tour essentially. So, the cheap edge here is for example between Chennai and Bangalore. So, I have now, I will just draw it a little bit this side because I want to write things here. I have two successors to this, one I will call CB and the other I will call CB bar, and by this I mean I have partitioned the whole set into 2 subsets. In one subset which I call CB, the Chennai Bangalore segment will always be present, and in the other subset it will always be absent essentially. Now, I want estimated cost of these two things. So, for every node in my search tree I need an estimated cost, exactly like what is happening here. Now, you can see that, so let me write it here, CB here, CB bar let me write here, and CB here. Now, you can see that CB will not change, because I am going to include this lowest cost edge. I have already done that in my original estimate. So, whatever was my original estimate will continue there essentially. So, for that case I can just copy these figures from here. But for CB bar I cannot do that. Why? Because I have excluded the edge CB from that set essentially. So, I have to find revise. So, I can't use 300 because in this that node C this thing. So, can somebody tell me the value for this? I think so we can use that divided by 2. 3550. So, this cost is 3550 and this cost giving will also be 3550, but this cost is not going to be that, because I cannot use this 300. So, I have to use the next 2 edges, which means 600 and 1000, which means this will go up by 700, right. So, I will write plus 700 here. I cannot use this here. So, I have to use this. So, instead of 900 it becomes 1600, which is plus 700 here. Instead of 800 this becomes 1400, which is plus 600. The rest will not change because I am not using that edge here essentially. So, that is 1300, and when I divide by 2 I will get 650. So, this will be plus 650. So, I have a way of devising edges essentially. So, what have I done? I have said that, so this is Chennai, then this is Bangalore, this is Hyderabad on some scale, this is Mumbai, and this is Delhi here. So, I have said I am going to add this edge, and that is my set CB. So, all tours in which this segment is there I will call CB, and all tours in which this segment is not there I will call CB prime. Out of these CB seems to be better. So, I will refine that, and let us say I follow this heuristic. It is not necessary to follow this heuristic, but let us say we follow this heuristic, which is always pick the cheapest available edge. It is like a greedy algorithm which tries to build cheapest tours essentially. So, I look around my this graph here, and the cheapest tour I can find next is 500, which is between Hyderabad and Bangalore. So, what am I doing now? I am saying add this edge, and I am refining this graph. So, one side will be called Hyderabad and Bangalore, and the other side would be called its complement. So, the way to interpret this node is that this HB prime node is that all those tours which contain the Bangalore Chennai segment, but exclude the Hyderabad Bangalore segment. And the way to interpret this node is all those tours which contain both the Chennai Bangalore and the Hyderabad Bangalore segments. So, that is what I have drawn here, all tours which have this two edges is this. So, now let us find an estimate for this. How do I do this? So, at this point I should mention before we do this process of computing the estimates is a computationally intensive process, in the sense you have to spend some computation time looking at this matrix and doing some things, but there is also that you can do a certain amount of reasoning, something that we would call constraint propagation in the process of doing estimates. So, let me illustrate that. So, let us, so first of all, because we have chosen the cheapest edge, then for this node HB I am anyway going to include both these. So, it is not going to affect my cost. So, the cost for HB is not going to change. So, you should just convince yourself that is going to be 3550 also, but this cost for HB prime that is going to change. So, let us look at the change essentially. So, one thing is of course that you cannot use this Hyderabad Bangalore link, which is this is Hyderabad and Bangalore. So, this link, so this link I cannot use, just as we did for CB prime, for this node also we cannot use this link. So, which means now this will become 300 plus 900, which is 1200. Originally I had 800, now it is 1200. So, if you compare with this as the basis, I get plus 400 here, and likewise here I cannot use this 500. So, it becomes 600 plus 700. Originally it was 1100, now it is 1300. So, it is plus 100 here. So, I am just adding the incremental cost, only these two rows will change, plus 200. But coming back to this, how see we have this desire and we will see this in the next class, that having an accurate estimate helps, or if not in the next class then in the class after that, that the higher the estimate the better for us, and intuitively it means that the higher my estimate is, the more likely it is that it will get excluded from a search space essentially, if I find a cheaper solution. Now, if you look at the estimate for this, I have this Chennai Hyderabad section. Chennai Hyderabad is this one, this 600 and this 600. Now, if I do a little bit of reasoning or constraint propagation, and what is the constraint I am propagating is that I want to find a complete tour, which means that I cannot have a cycle which is smaller than length 5 in this example. I cannot have a cycle of length 3. So, if I am going to have that set H B which includes, so actually yeah, it means that this estimate is not correct, even though I wrote it there. Why is it not correct? Because I cannot include in my estimate this Hyderabad Chennai sector. Why? Because I have already included CB, so in that path, and then in this path HP. So, I am talking of this node here, and I am saying that even the estimate of this node will go up, and the reason why that will go up is that having included CB and having included HB, I am forced to exclude HC from that, because otherwise I would have a cycle of length 3, which means I cannot use this value for computing this for this one. For computing the estimate of that node, I cannot use this value 600. Instead, I will be forced to use the next value, which is 300 plus 1000, which is become 1300, which is of course more reasoning than what I did so far. What I did so far was, if I am including an edge, I cannot count it when I am using those bar kind of nodes essentially, because they are excluded. Sorry, if I am excluding an edge, then I cannot count them. But now we see that there is certain propagation which takes place, that if I am including this edge and if I am including this edge, I cannot count this edge. So, let me just draw a zigzag line to say that I cannot count that edge. Why? Because then I would have a cycle, and I can go to more extent, to do more reasoning to get better estimates. And what do I mean by better estimates? Higher estimates essentially, which means if you cannot include something, then do not include it, and that something in this example is 600 here, which is a low cost in this row, also in this row, but I cannot use it in my estimate. So, I must use something else which will give me a higher estimate. Another edge here that I cannot include, after I have included Bangalore, Chennai and Bangalore, Hyderabad, there are two more edges that I cannot add, because I want a tour, and the tour has this property that every city is visited exactly once, which implies that every city has exactly 2 edges incident on it, and I already have Bangalore which has 2 edges incident on it in my this set. So, I cannot have this set, neither can I have this set. So, you can see that problem solving is does not necessarily a one pronged strategy, that you just do search and only search essentially, and later on we will see that it is often useful to combine search with reasoning essentially, some amount of reasoning and some amount of search, and in the process you will try to cut down on the search space more and more essentially. What do we gain by excluding this? We get more accurate estimates. So, for this tour called HB, which is the set of all tours which include, now we can describe it more specifically, saying that HB stands for the set of all tours which include that path here, that CB edge, the HB edge, and which excludes HC, DB and MC essentially. So, already we have narrowed down our choices and made better estimates essentially. So, this is the same thing that we were doing here, refining the least cost partial solution. So, we started with 3550 and then we got two solutions, one was 3550 and the other one was a bit more than that. We refine this, we get these two solutions. We have not computed the actual cost for this, but once we do that we will refine them and at some point we will get a complete solution. So, for example, in this problem, if you were to add one more edge, let us say this edge, Hyderabad to Mumbai, then actually you have solved the problem completely, because then after that you do not have any more choices left. If you are going to include these three edges, then you have to visit Delhi once, and once you have to visit Delhi from Mumbai and once from Chennai. So, the rest will be forced essentially. So, after we have done this search, we have found a complete tour after we added this search. So, below HB if we add MH, and if this node MH, which includes these three edges, happens to be the lowest cost node in my search space, then I can terminate. That is the shortest path I have found. So, you must convince yourself that this termination criteria is sound. By that I mean that it will guarantee an optimal solution essentially. And one of the reasons behind that is that I have said that we are going to use lower bounding estimates for estimating the cost of a solution. You can see that there is some similarity of branch and bound with breadth first search essentially. You can view breadth first search as doing branch and bound with the condition that all edge costs are equal essentially. That will force the, if all edge costs are equal, then you will just go down level by level, because the first level the cost is 1, the second level the cost is 2, the third level the cost is 3 and so on and so forth. So, breadth first search is a special case of branch and bound, where all the edge costs are equal. When the edge costs are not equal, then branch and bound is a specialization of breadth first search in that sense. Sorry, it is a generalization of breadth first search. So, you have to convince yourself that this will give you an optimal solution, but it does not have this. Of course, I said we are going to use a heuristic that use the minimum cost solution, but it does not have a sense of direction essentially. So, let me illustrate that with a very small example, that if you are doing this city map kind of a thing, and if this is your start node and this is a map that you are looking at, and this, let us say this is to scale, which means the length of the edge that I am drawing is actually the length of the edge. So, let us say you have some such place. So, you are at the start node, and then of course, there is one node here, let us say, and then some nodes here, and let us say this happens to be your goal node. What will branch and bound do? What is the behavior that branch and bound will exhibit? It will explore all this part of the graph, because that is what its mandate is, extend the cheapest partial solution, and all the cheapest solutions are on this side of the graph. So, it will explore this, it will explore this, it will explore this and all possible combinations, which of course, as a intelligent viewer you would see is not a very bright thing to do essentially. It will guarantee eventually it will find me the optimal solution. For example, if there is another path from here which goes like this, which is longer, it will find me the shortest path, but after doing a lot of unnecessary and useless search in this part of the map essentially. It does not have a sense of direction. We are focused on this part, finding optimal solutions, and in the process we have forgotten about this part, finding solutions faster. So, in the next class we will combine these two together, and we will see that how we can combine branch and bound with, this was best first, if you remember, best first search. We will introduce a heuristic function back again and try to use this Dijkstra's framework of working on a graph to look at an algorithm which is a very well known algorithm called A star algorithm. So, I will stop here and we will take this A star algorithm up in the next class.